Yeah, so KVL comes from another Maxwell equation, which is uh, which is called the curl of E equals to um, in this case is 0, but that's assuming there is no uh, change of electric field in this loop. So if you don't have any change in the electric field in this loop, then what's called the curl of the E, or the integral of this line, is equal to 0. So what I should really say is that this equation here, n close by to 0, is actually comes from Maxwell's equation, assuming that in that loop there is no change in magnetic field or electric field. Then that'll get satisfied. So that, and in our circuit that is usually the case, because the change in the varying current, time varying current, which is going around in the loop, typically that is so slow varying compared to the dimension of this, that you don't have any huge change of electric field. So then this always holds. If that's not the case, like in RF, for example, if you have a big circulating current like 10 gigahertz, this is not true, because this will be equal to whatever is the change in electric field inside it actually. Okay, so what do we use these laws for? Like um, so most of these laws we are going to talk about now is to analyze, understand, and design linear time invariant systems. Okay, so everything you're going to design or analyze or anything, they're all nonlinear system. Nothing is linear in this whole world. I mean, even a resistor is not a linear system actually. But obviously, the tools required to analyze nonlinear systems are, you know, there are only like Nobel laureate people who use those tools to analyze those systems. But luckily or fortunately, most of these nonlinear systems, they are linear in the kind of domain we want to analyze them. So then we can use all the linear system tools to yeah, sort of analyze them. So what I'll do is I'll just quickly explain what a linear system means, and that's, I think, was the key part of the question which I was asking for that diode capacitance one. Uh, so linearity, like, when I asked you on that day, I think Abhinav answered that question correctly, that using superposition. So I'll explain. I think everyone is aware of what superposition is, so I'll just quickly explain that. So this is in words, but I'll just show you in figures. Essentially, what superposition means is that if you have a linear system, for example, in this one, I'm considering H as this linear system, then if you apply a input and you get an output. So for example, if I apply input, time varying input, or non-time, I mean constant input I dash of t, and I get output v dash of t. Then I take the same system and I apply another set of input, time varying input, I double dash of t, and the output is v double dash of t. Then basically the superposition principle says that if the system is linear and then I take any linear combination of this, where a and b are um, any real integers, I mean any real numbers, not complex but real numbers, then the sum of that will also be the same linear combination of the respective outputs, which is a times v dash of t, a plus v dash of t. So that's superposition. And so they are reciprocal in nature, in the sense that um, if your system is linear, you can analyze systems by applying superposition. For example, applying um, Fourier series to a system to analyze arbitrary signal is because it is a linear system. That's why you can linearly sum all the outputs, right? So for example, if you want to analyze a square wave of a system, or any arbitrary signal, you know that any arbitrary signal is a combination of sine waves. So you can actually do um, response of every sine wave and add them up together, and that gives you this response of the entire system, right? So that comes from linearity or superposition. But if it is not linear, then you can't apply it, right? Because then if it is nonlinear, then you can't do superposition. So if a system is linear, then you apply superposition to analyze a system, but it is also reciprocal in the sense that uh, okay, there's a question, does H here indicate that H parameter or linear? No, sorry. It's just means a system, a linear system, nothing to do with H parameters. I just named this H. So basically, you'll write it H of S or H of F or whatever it is. So yeah, it could be F, it could be S, it could be A. I'm just saying it's a linear system. Okay, now the thing about superposition principle and linearity is that you can also apply superposition principle to figure out if a system is linear or not, right? So like I was asking you the other day, is the diode capacitor a linear system or a nonlinear system? And if you are in doubt, like for example, capacitor, right? How many of you think capacitor is a linear element or a nonlinear element? Quickly, capacitor. Okay, Abhinav says linear. How about the rest? Linear or non-linear capacitor? Quickly. Just tell me what your intuition is. You don't have to prove it right now. What have you been thinking so far? Is capacitor a linear element or a non-linear element? Linear, 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 non-linear, non-linear. Yeah, just tell me what you have thought so far. Non-linear. Okay, go ahead. Just tell me what is linear and non-linear. Okay, so I think it's almost half-half. So let me ask you this now. The people who are saying it is nonlinear, why do you think it's nonlinear? So let me maybe ask. So Sandhya Rani, let me ask you, why do you think it's nonlinear? I think you should be able to unmute yourself. Or yeah, you can write.
Hello.
Yes, I can. Yeah, go ahead.
The capacitance VI characteristics at the time after breakdown, it will start from some positive value. So it is not passing through the zero line. That's why I think that it is non-linear.
Yeah, no, so forget breakdown. Breakdown is like, that's like talking about second order effects, but just a pure capacitor, right? So yeah, and so basically you're saying the VI relation doesn't pass through zero, and that's why it is
Yes.
nonlinear. Okay, and that's the general sort of intuition why people think it's nonlinear. Uh, but the and that's where when you come to a system, if I ask you if a system is linear or not. And obviously, when I give you a resistor and you say, okay, yeah, the VI relationship is, um, you know, looks like linear, that's why linear. But that's just a hunch, right? It's not a scientific way to tell if it is system is linear or not. So I think you're saying, okay, if I do a VI relationship between um, I and V relation with capacitor, it's actually just zero all the time, right? Because there's no DC current flowing at all. So you're saying it's nonlinear. But that's not why it is nonlinear, right? You can't say from that it is linear or nonlinear. Obviously, if the response happens to be nonlinear, it has a B square term, then you know, obviously. But some of it is like capacitor is a good example. So what's the equation for capacitor? So if you have a capacitor, what's the current equation or voltage equation? I equals to C dV over dt, right? So the real way to find out is if superposition applies to this, what I call it is the constitutive relationship, right? Between V and I. If there is a, yeah, if you had I equals to some K times V, and you said K is a constant, then this one is obviously, linear, because by definition, this is a linear equation. But here it is not that straightforward because you're looking at I and there's one is a derivative and you're thinking, oh, is it linear or not linear? So you apply a superposition principle. So whenever in doubt, you just apply superposition principle, right? And then for superposition, you'll see that. So now I apply a voltage V1 and the current is I1, which is C dV1 by dt, right? I apply another voltage called dV2, I mean time varying voltage, obviously, because DC. So this is I1 of t. Then I apply another voltage, then this is TV2t, then the current is I2t, let's say. Now if I add both of these together, V1 plus V2, right? And if I take C d dt of this thing, is it equal to I1 plus I2? And it is, right? If I add these two together, then it is this. So that means this is a linear system, right? So that's how you know if a element or a system is linear or not. You just apply superposition. And so that's why I said it's a reciprocal principle, in the sense that if you know a system is linear and you want to analyze, you apply superposition. If you don't know if a system is linear or not and you want to find out, you apply superposition also to prove it. Like for example, a diode, right? So diode equation is, so I1 would be equal to IS, let's say e to the power V1 over Vt. I2 is equal to Is times V e to the power V2 over Vt. Now, I1 plus I2 is not equal to Is times e to the power V1 plus V2 over T, right? Because this expression here is I1 times I2, not I1 plus I2. So that's why this is nonlinear, correct? So, so you apply superposition to basically prove a system is linear or nonlinear. Okay, clear? Any questions?
Sir, what if the dielectric which we have in the capacitor will a ferroelectric substance?
So you tell me what is this equation then? Yeah, I don't know what ferroelectric does. So is this still valid?
Yes, sir.
Then it is linear. Okay. But actually the ferroelectric, this is not valid because this is a function of V. Okay. If this is a function of V, then you'll see that it, applies superposition, then it doesn't valid. So that's why it's nonlinear. So when you said, is it C dV by dt, you actually answered it incorrectly, saying that it's not. It is probably a function of V. So the capacitance is changing as a function of V, just like the diode, right? So the diode is like C as a function of V, same thing, dV over dt, right? So if that's the case, then I1 plus I2 is not equal to, because you can't say that this is CV. Uh, Yeah, you can't say that it is C of V1 times dV V1 plus V2 dt of that, or V2 or whatever it is, some X value, because you're trying to say that this is constant. If that's the case, then this should be valid, but it is not. It is a function of V, so then you can't use it, right? Is there any, excuse me, is there any relationship between superposition theorem and superposition principle? They're the same. Principle or theorem, they're the same. Okay, so the time invariance principle is, you don't use this in circuits, but it's just good to know. So when you apply all your linear system equations, you are actually applying it to linear time invariant systems. You're not just applying to line linear system, because and essentially what the time invariant system tells you is that if you have a system and you give an input and you give an output, you delay that input by some amount t, then the output also gets delayed by t. Okay, so which I have explained in this here. So if you have a relation I of t and v of t, then if you delay the input by amount t, capital T, then the output also gets delayed by t. If it is not, then that is time variant system. If it is a time variant system, again, you cannot use any of these principles. like I said, most of the things you are using is not, so you don't mostly don't have to worry about it. Okay, so I'll just quickly introduce the circuit elements, which obviously all of you are familiar with. And so obviously everyone knows resistor, and it's just a Ohm's law which defines it, defines the relationship of current to voltage. The constitutive relationship is basically the relationship between voltage and current for these elements. And usually a lot of times when you're doing circuit analysis, it is much easier to express the resistance as conductances, which is inverse of this, so that you're not carrying reciprocals all the time. And for capacitor, I think again everyone is used to the constitutive relationship where the current is C times the derivative of the voltage. And if you want to find the voltage, then it's the integral of that current. But then when you're doing that, then you need to know the initial condition as well. Same thing with the inductor. It's the voltage is L times the derivative of the current flowing through it. If you want to find out the I, it's the integral. But then again, you won't need to know the initial condition, initial current through it. So these are basically the three elements we'll be dealing with. And like as I said, in IC design, we typically don't worry about inductors at all because they're just tiny. So it's usually resistors and capacitors. For the independent source, the independent sources are also a part of linear systems. And essentially what you have two types of independent sources, voltage source or current sources. And the voltage sources is basically saying doesn't matter what current is flowing through it, the voltage across it is same. So these are ideal, what's called ideal independent voltage sources. So if I draw the IV characteristics for this, then it's basically a line V from minus infinity to infinity. So this is, sorry, this is the ideal voltage source. 1 second. So if this is V, this is I, then your IV characteristics is this, going from minus infinity to plus infinity of I. So essentially it says no matter what the current is flowing through it, the potential difference between these 2 points is always V, whatever V you have chosen, V or V of t. Same thing about the current sources, ideal current sources, independent current sources. And so if I draw the IV for this one, obviously it's going to be a parallel one with V. Basically, it tells you that no matter what the voltage across it is, the current through it is always, whatever is that independent current source you have chosen. And uh, the other elements you deal with in circuit theory is the dependent sources. Circuit analysis of dependent sources. We use this a lot for modeling different devices. So these are basically control voltage sources or control current sources. So you have basically two um, sort of independent controls like voltage or current, and the output is again a voltage or current. So you have two control elements, two independently output elements. So the combination of that are basically four elements, and those four are, the first one is what's called a voltage control voltage source. So you can see this is a voltage control voltage source where the output voltage is some alpha times, which is a real number, times whatever is the input voltage. Okay, and in ideal VCVS, this is input impedance is infinite, which means that you're not drawing any current from this source which is driving these two nodes. And the output impedance is zero, in the sense that the output voltage is always alpha times V1T. Doesn't matter what the current is flowing through it. Okay, so it's basically the output looks like an independent source, but it's controlled through these two. And typically, op amps, for example, is we will model it through this VCVS. The voltage control current source is your the output current is some G times, which is again a real number, times V1, which is the input V. So your output current is dependent by some constant times the input V. And this is called the voltage control voltage source, or it's called a transconductance element, right? And in fact, your transistors, MOS transistors, If you want to do ideal MOS transistor modeling, that's how you model, because that's a ideal transconductor, right? Like what we derived today, the output current is based on the gate current. So this is obviously a linear version of that. Current source is output current is some um, um, R times the input current flowing. And in this case, no matter what, the input voltage here is 0. So it's an ideal like short, and whatever current is flowing through it, the output is a, some R times that I is the voltage output. Okay. And again, same thing, no matter what the current is flowing through this, the voltage is always R times I1T. So output impedance is, so here the input impedance is 0, output impedance is 0. Here input impedance, so if I look at R in, this is infinite. If I look at R out, this is equal to 0. Here R in is equal to infinite, R out is equal to 0. Here R in equals to 0, R out is also equal to 0. And then the last one is um, current control current source. So this one, current control voltage source, is you can um, model what's so this is a trans impedance element, so you can model trans impedance amplifiers. So a lot of sensors, for example, they are current in and you want to convert to voltage. So this is a good element to model that. Current control current source, again, you take a input current, so your Rin is equal to 0. So it's a short, and you monitor this current, and the output is some beta times, some real number beta times this input um, uh, current. And the output um, impedance is also, sorry, I think I made a miss. Output impedance is infinite. Sorry, this one is output impedance is infinite as well. It's a current source, so the output impedance is infinite. Um, okay. So these are just the control sources. So these are basically what is 3 plus 2 plus 4, sort of 9 sort of elements we use a lot in doing linear system circuit analysis to do that. Okay, I think I'll just quickly talk about the node equation method to solve equations. I think everyone is again aware of, but I'll just sort of introduce it. So if you have a network with n, for example, nodes in it, then you can apply KCL, KVL to all those nodes, and you're going to get n sort of voltages, n currents. And so essentially you get two n independent equations with n branches of the circuit. So you can solve all of them, but usually you solve it using this node equation method. And I'll show you an example that'll kind of make it more clear why we use this one. So the node equation method is, instead of doing KCL and KVL on all branches and all KCL on all nodes and KVL on all branches, what you do is you pick a reference node. Okay. And how do you pick a reference node? You can arbitrarily pick it, but sometimes it is best you pick a node which you think is sort of the lowest potential node. So for example, if you have a circuit, a passive circuit, and you have a voltage supply, then you take the negative end of the voltage supply, the lower potential of the voltage supply, as your reference node. If you do that, then all your numbers come out to be nicer. So so you can um, you know um, logically pick any node, but picking a better node actually makes your solutions or analysis tractable. Okay, then after that, what you do is you assign node voltages to all nodes except uh, to the nodes of the ideal sources. So if you have a voltage source, for example, we'll do some examples, it'll be more clear. And if you have a voltage source, you don't need to assign unknown voltage to both ends, because you know that if one end is V1, the other one is V1 plus V. So you don't have, that's not unknown. Um, and then you write the KCL equation for all the assigned nodes and you solve it. Okay. So let's take an example here. Um, so you just have a simple voltage source in series, two series resistance on both terminals, and there's a ideal current source right across it. Okay, so let's see how we can solve this using the node equation method. So like I said, if you were using blindly, then you take the 4 nodes, apply the KCL, one branch, and you're going to apply all of that and try to solve it. But if you use the node equation method, you'll see that it is a little simpler. And here, um, okay, so okay, I guess I thought I had. So let's see how you're going to solve this. So let's pick a reference node. What is the reference? What reference node should I take? Like as I said, pick a node which will give you tractable answers. So for example, in this, I know this is most probably going to be there is another active element here, but I know because the current is flowing in this direction, so this should be probably the lowest node. So I can pick this as the reference. Like I said, you can pick any of these 4 node as the reference, but then your answers will be more tractable if you do this. So you do this, and then like I said, you don't have to pick this node because I know this node is V naught if I pick this as the reference. Then basically I have just 2 nodes, right? I have this node here. So let's name this node V1. Let's name this node V2. And then you write the KCL for this node. So the KCL at this node is V0 minus V1 over R naught is equal to I naught, and then you write the KCL of the V2, and that will be V2 over R1 is equal to I naught, and you basically now you have 2 unknowns V1 and V2 and 2 equations, and you just solve them, right? So for example, you can just substitute I naught here, V2 equals to and V naught minus, yeah, I'm so V2 equals to I naught R1, and yeah, actually this is pretty straightforward, right? So you get V2 equals to I naught R1, and V1 minus V0 minus V1 is equal to I naught times R0, and so V1 is equal to V naught minus I naught R naught, right? So those are your 2 unknown voltages. So that's the node equation method. So let's do this exercise. So let me allow you guys for a few minutes, and then we can discuss. So just try this out. So use the node equation method. Remember the 3. You choose the reference point and choose all um, the nodes except the independent voltage nodes, because you know what the other side of the reference is going to be. Then write the KCL for other nodes and solve it and find the solution. So just try this one out, and I'll give you guys a few minutes, and then I can discuss.
Sir, can you move to the previous slide, please? Okay, sir. Thank you.
Okay, so first answer is 4 volt with respect to ground. Which one, Abhinav? V1, V2, V1 minus V2. Okay. All right, let's see. Okay, Jackie says V1 is 4 volt with respect to V2. Okay, good. So Rudra says 4 volt with respect to V bat. V bat, the which node? The 10 volt node, we mean? Okay. Okay, so one says V1 minus V2 is equal to 4 volts. Okay, I hope rest of the people are trying it out. Try it out, even though it seems very simple. Try it out. Okay, so looks like everyone's saying V1 minus V2 is 4 volts. Okay, let's check. So, all right. So, what was the first step? Pick a reference node, and what is a good reference node to pick here? Actually, V2 is the good reference node to pick here, right? Because that's the negative side of the battery. So that's why you didn't have to. If you take that as a reference, then you just say V1. So V2 is 0 volts with respect. I mean, that's your ground. That's your reference ground right now. And this one, you don't have to do anything because you know this is going to be 10 volt because this is the ideal source. So you're left with only V1, just one node, right? So you write the equation, KCL equation for this and just solve it. And so if I write the KCL, so on V1, so let's say this is the incoming current. So I'll say that's 10 minus V1 over 10K is equal to 0.2 milliamp plus V1 over 10K. Right, so that's, and you just have one equation here. So you solve it, and so basically you'll get 10 minus V1 equals to 5 volt. Um, oh, sorry, this, yeah, 5 volts plus V1, or I'm making a mistake somewhere. 10 minus V1 over 10K is 0.2 milliamps plus V1 over 10K, and then 10K times 2 is 5 volts. 10 minus V1, so 2V1 is equals to 5 volts. V1 is equals to 2.5. I'm sorry, yeah. I don't know why I'm thinking. Yeah, thanks, Avinav. All right, so 2 volts times V1, 2V1 is equal to 10 minus 2 is 8 volts, and then V1 is equal to 4 volts with respect to, because this is your reference node, so I don't have to tell with respect to V2. Okay, so I think everyone got this right. All right, and other thing I wanted to point out is, when when you solve circuits like this, if you're getting, so for example, the reason I knew I was wrong is 2.5. Or I shouldn't say wrong. You can do sanity checks, right? First of all, obviously, you guys were saying all 4 volts. I trusted you guys. But, for example, if I remove this current source, I know this is 5 volts. And if this is zero point 0.2 milliamps, um, times 5K, I know that's going to be 1 volt. So it should have been 4 volts. So that's why I knew it was something wrong. So that's why you should always know how to do sanity checks. And this is where you can use superposition as well, right? So how do you solve this using superposition? This is a linear system. How do you solve this using superposition? So in superposition, your two independent variables are this, right? The VBAT and your current. So in the first case, you say, I want to remove this. And if you remove the current, these two nodes will just be open, right? So your output V1 is equal to 5 volts, right? That's basically 10 volt divided by 10K, 10K. In the second one, you have just the current source, um, but you remove the battery. But when you remove the battery, what you mean is you're making VBAT equals to 0, which means you want to short it, right? If you short it, then this one is the current source with 10K, 10K in parallel, so you get 5K. So the um, the current which is flowing is actually in this direction. So you get minus, it's zero point 0.2 milliamps, so it's minus 1 volt. So V1 equals to minus 1 volt, right? So if I add them together, so let's call this V1 dash, V1 double dash. So then V1 is equal to V1 dash plus V1 double dash. So that's 4 volts too. So for simple circuits, you can always apply superposition to get your answers as well. If that makes sense, everyone agrees with this or have any questions on the superposition? I think the node equation part, everyone got it? Okay. Can we apply source transform? What do you mean by source transform, Swadesh?
So like converting that current source and the resistor parallel with that into an voltage source with series resistance.
Yeah. Yeah, we'll get to that. Actually, we'll get to that. You can. All right. So here I again show, kind of the difference between using the KCL KVL method, like the brute force method, and using the node analysis, like why doing hand calculation using node analysis is a more efficient way. So if you take this circuit here, for example, so this is kind of a Bridgestone circuit, and you can see that you have, I mean, 5 branches, 1, 2, 3, 4, 5 nodes, right? No, yeah, sorry, 6 branches, 6 nodes here. So you have totally 12 unknowns. So you find out relationship. First, you do the element relationships. So basically, V1 equals to I1 R1, V2 equals to I2 R2, and so on. You find the 6 equations from that. And then you have 6 nodes. You get 3 equations from each, 3 KCL equations from the 3 nodes. Um, you know, why is it 3 nodes? Oh yeah, because you have taken, this is the same current as this. So yeah, so you write KCL at 3 nodes, and then you have 3 branches, 3 KVL loops basically. So you have one loop. 1 second, control. So yeah, so and you have 3 loops here to write 3 KVL equations. So you have 12 unknowns. You write 12 equations and you solve it and you get it. So, but obviously you can see that if I apply the node equation method. So we start with this as the reference node, let's say. Like I said, again, if you have a voltage source, take the negative part of it and that becomes your reference node. And this one I don't need because that I know obviously it's V naught. Then I'm left with 2 nodes, right? So I write the KCL equation of the 2 nodes and I solve it and I get the answer. So instead of doing 12 unknowns, 12 equations, solving 12 equations for 12 unknowns, you reduced it to 2 equations and 2 unknowns. So that's, why we use that method. Okay, so like what Sudesh was asking, node transformation. Yeah, you can do that, and usually the theorem you use or the method you use is the Thevenin's or the Norton's method. So if you have a linear circuit, like let's say this is a linear circuit with a lot of linear elements in it, all the linear elements I showed you, then you can represent this entire circuit as a Thevenin equivalent, like this, where you have a voltage source in series with a resistance. And there is a corollary for this also. So you can, if this is, because capacitors and inductors are also linear elements. So if you have that, then you can do the S domain for it. So this will become VTH of S and Z of S actually. So impedance, instead of resistance, it will be impedance and frequency dependent, I mean, a voltage source, um, like a Fourier transformed voltage source, basically. So that's so you can definitely use this in RCL circuit if you express them in S domain. Basically, if you have it in differential, it's much more cumbersome. So if you convert it into S domain, then this will become VTH of S and RTH of S, basically. So the Thevenin applies to that as well. And so what's VTH? VTH is the open circuit voltage at these two terminals. So open circuit in the sense you don't apply any load. So no load. So it's the voltage when there is no load. So there are no loads applied, and you measure the voltage like with a voltmeter, right? So if I have a system, I apply the voltmeter across this. And so that's my VTH. And RTH is the impedance between these two terminals when all the independent sources in them are zero, not dependent, just the independent sources, which is the voltage and current source. So you make all the independent sources zero, measure the impedance or the resistance, and that's your RTH. So all independent sources zero means voltage sources are short, current sources are open, just like what I did in the previous example. In the previous example, um, when I was doing superposition, I made the voltage short and current source open in one case and applied the current source and made the voltage source short in the other case. So that's because I'm making independent sources zero at one time and adding the other independent source. The sort of the mirror or the um, kind of the reciprocal of that is the Norton's method. In the Norton's method, you can convert um, the same circuit which I showed you before to a equivalent circuit which is a current source in parallel with the impedance. Guys, just give me a second, 1 second. Okay, sorry, I'm back. So yeah, so Norton is similar to Thevenin, where you take that, for example, the same network we did before, and the Norton equivalent would be a current source in parallel with a resistance. And same thing applies here. The corollary of that is if this has capacitors, inductors, you can convert them into S domain. So then this will become ITH of S, which is a function of frequency, and RT, this will become a impedance, which is basically a function of frequency as well. So, and it'll have magnitude, phase, and all that, just like the way you analyze um, S domain circuits. And how do you find out these elements? So ITH is the short circuit current. So you actually short this node over here. You don't do any zero stuff inside. You just short it, measure the current. That's your ITH. And you for the RTH, it's the same as the Thevenin's method, where you make all the independent sources zero, which means voltage source is short, current source is open, and then you measure the impedance, and that impedance you put it across RTH, not in series, but across. And you can see that from the Thevenin's equivalent as well. So if you look at this Thevenin's equivalent, I can take this Thevenin, and if I do a Norton equivalent of this, you'll see the short circuit current is ITH is equal to VTH over R, right? So this will become VTH over R. And then in order to find out the RTH, I make this zero and it is RTH, right? Which is the RTH here. And you can do the opposite. So now if I want to do the Thevenin of this, then I do the open circuit measurement of this. So then ITH times VTH. So I should show the current direction in this actually to be consistent. So the voltage drop across this is I times RTH, which is obviously VTH was ITH was VTH over RTH. So now it is ITH times RTH. And the impedance is I make the independent sources zero. So I remove this. So it's open because it's a current source. And then I measure this, which is RTH, right? So you can see that they're reciprocal in nature. So I can do a Norton equivalent or a yeah, Thevenin's equivalent, and they're the same. So the question is, if I want to analyze a circuit and I want to simplify it and do analysis, which one do I use if both of them are equal? It really depends on the application. Okay, so typically you use the Thevenin if, for example, let's take an exam. So let's say you want to find out, um, a certain amplifier. I mean, just so you have your cell phone and you had your head jack and you're trying to put an amplifier here, right? And you want to see if this amplifier is capable or your cell phone is able to drive this amplifier or not. In this case, you want to do a Thevenin's equivalent of your entire cell phone. I mean, just the driver, right? So what you want is you have amplifier, right, which has input and output, and this is usually very high input impedance. Rin is basically ideally infinite. So if you have if your circuit is driving a very high output impedance, then typically you want to do a Thevenin's equivalent. So your cell phone will look like this. So VTH and RTH, or VTH of S and RTH of S. And then you can analyze the system. You can say, okay, there is an input impedance of Rin, blah, blah, blah. Signal level is going to be so and so. And then you can analyze it. Now you can do a Thevenin's and do it also. But like as I said, it's easier to do Thevenin. I mean, you can do a Norton and do the same thing too, but it's easier to do Thevenin. Same thing in Norton, it's the opposite. If your input is like, for example, sensors, right? So if you have, for example, a water sensors, okay, most of the water sensor, the output is actually a current, right? If the output is a current, it's best you actually represent this as um, a Norton, because if the output is current, you usually will be using a transimpedance amplifier to amplify the signal, converting current to voltage. So if you have a Norton equivalent of this, then it's easier to just analyze the whole circuit. Okay. Again, you can do a Thevenin's also do it, but then you have to do VTH over RTH, find the current, and then do it. But here you actually get the current directly, and what is your output impedance. So it's more natural to that system. So yeah, it depends on the system. So if your output is current, usually you would like to do a Norton equivalent of this. If your output is a voltage with a very low impedance, then you do Thevenin's equivalent. Okay, so let's do an example. So I'll give you guys a few minutes here. Let's do both a Norton and a Thevenin equivalent for this one. So you're trying to find out So basically, I want to represent this part here as a Norton and a Thevenin equivalent. Okay, so first you want to convert this into this. And then convert this. So this is a Norton equivalent. Okay, so I'll give you guys a few minutes, try it out. Okay, a lot of answers. Good. A lot of people trying. Looks like everyone does the RTH first. um, yeah, I think everyone got the RTH right. So, all right, let's do Thevenin's first. So how do we find VTH? What is the method? That's the open circuit voltage, right? So open circuit voltage for this one. Now you have two independent sources. You can solve like node equations to find out V1 minus V2, which you already did. Or you can, so we have already solved this equation, right? So you can use that directly. So VTH, or you can just apply quickly superposition, right? So when the current source is when the current source is off, which is open, then this voltage is V naught, right? And when the current source is on and V naught is shorted, right? Independent sources is zero, means voltage source is short here. This is shorted. Then because the current is in this direction, then the voltage is I naught. So VTH is equal to V. So that's your first superposition value. And then minus of I naught times R1 plus R2, correct? So that's your VTH. And RTH, obviously you find the resistance. There is no capacitance or inductor, so we just find the resistance. So you make all the independent sources zero. So you open current sources, short voltage sources, and then this is R1 plus R2, right? So I think that one everyone got, R1, R2. All right, so that's your Thevenin equivalent. And if you want to be really lazy or cheat, you could have made your RTH as this, right? So you could, or don't cheat, but at least to cross check. So now let's find out the Norton equivalent. Let's say you didn't know the Thevenins. You find out the Norton equivalent. So Norton equivalent, say ITH, right? So ITH is you short circuit this, and you find out what this current is flowing in this direction or the opposite direction, whatever convention you choose. So here I've shown it in this direction. So let's keep it current in this direction. So ITH is now same thing. You can apply superposition. So if you apply superposition, you can see that when I disconnect this, then the current is in this direction, which is V naught divided by R1 plus R0. Then you then you short this and um, apply the I naught and then measure it. But the thing is that if you short this, doesn't matter what R1, R2 is, because you have a short circuit, all your current is going to flow through the short circuit, which means that it will be minus I naught. That's your ITH. And RTH is obviously the same because you open circuited just the way you measure it, right? R1 plus, sorry, R0 plus R1. R0 plus R1. Okay, and if you wanted to check if you made a mistake or not, these two should agree, right? And obviously RTH is R1 plus R0. And the way to check if this is agreeing is, you know that if you divide VTH by RTH, that should be your ITH, right? And VTH by RTH is V naught R naught by R naught minus I naught, because if I divide this by R1 plus R0, then this is this. So either you made two mistakes or you got it right. You made even mistakes or you got it right. Okay, but if they are not agreeing, that means you definitely have a mistake in one of them. So you got to figure it out. All right, so I think, okay, let me look at your answer, see if I've made a mistake. Hmm. So VTH is equal to V naught plus I naught R naught. No, I think you just, taken one voltage and added it, because there is a voltage drop on R1 too. So this is Praveen's. Then Rudra's is V naught minus R1, R1 plus R2, R0 I naught. Yes, correct. RTH is R0, R1. I think everyone got that right. Abhinab. is R0 R1, VTH is I naught times R1 plus R2 plus V naught. Actually, it should be negative because the current is in the reverse direction. Yeah, some of you got lazy, just wrote RTH, nothing else. ISC, Abhinav writes V0 by R0 plus R1. Yeah, but there's a minus R naught, I naught too, because you took only the voltage part. There is another short circuit current too. I mean the ideal source as well. Sandharanis is VTH V naught times I. Yeah, that's correct. Yeah, I think Praveen, you made mistake on both parts, so you need to correct it. Vijayalakshmi got, yeah, you got the Thevenin's part right. Yeah, Shivam Thevenin's part right. Yeah, looks like nobody attempted the Norton one. But okay, so you get the idea, right? Any questions on how we solve this? Okay, now give you another exercise. Can you solve this using node equation? This circuit here. So I want to find out the value of VD. Can you solve this? So I'll give you guys again a few minutes. All right, Sandhirani says yes. Okay, use node equation to solve this. So this, I don't know what is aim? Solve for VD, right? That's what I said, node equation, using node equation, solve for VD. The voltage across the diode is what I'm asking for. Or the current through it, whichever. Okay, so then it says V naught minus I naught R naught. Okay, what about others? Let's see. V naught by, people are just like throwing numbers now, I think. Okay, people still trying, or they've given up, or have only 3 answers so far. Do you have any questions you have struck here? I was expecting to get some questions. Looks like everyone is just finding solutions.
Sir, should we take the diode as ideal or real?
What is the ideal diode?
In like usually we take that as 0.7 volt, right? In silicon, the diode is a silicon
Yeah, good question. So, okay, if I give you the equation for it, like some IV, so let's say ID equals to IS times C to the power VD of T. By the way, who asked this question?
diode. Sir, Sumant.
Okay. Yeah, good question, Sumant. So yeah, no, don't put 0.5 now. You use the real equation and solve it. You know, the node equation method, I said. So let me ask you guys this question. If I give you that diode equation, so I've asked you to solve the entire circuit, right? Not in isolation, something. This whole thing is a circuit, and I want you to find out the difference in the voltage or the current flowing through the diode. And I give you the diode equation. Can you put node equation and can you use node equation and solve it? First answer me that. I mean, is it possible to do that?
No, sir.
Why not?
So it is a non-linear device.
Yeah, exactly. This is a
Diode.
nonlinear device, right? The diode is a nonlinear device. So why didn't you tell me? What were you trying to solve, Ashwini? So that's the first thing you guys should have asked me. Like, we can't use non-node equation here because there's a nonlinear element there, right? So everyone agrees that diode is a nonlinear element, right? We showed it when I was showing superposition. You can apply superposition and show that diode is a nonlinear device, right? So if there is a nonlinear device, you can't use node equation because KCL, KVL, node equations, Thevenin, all these are only for linear systems. Okay, you can't use nonlinear devices to basically solve it, because when you're applying superposition, the idea is that it is a linear system. If you have a nonlinear device there, then all bets are off. You can't use that, right? So you can't actually solve this. But someone asked a good question, is like, okay, can I take it as 0.5? because the diode, the voltage across it doesn't change a whole lot with the voltage. So that is what the first thing you can do is you can just substitute this as a voltage source of 0.5 volts and solve it, right? So that's what. So instead of trying to find out VD and ID for that, you know that you can solve it. So and the other method I wanted to show you is that what you can do is you can find the Thevenin for this, right? And then it's easy to calculate. So usually when you have a diode, you usually are trying to calculate the current through it because voltage, it's around 0.5, 0.65 volts. So you're trying to find the current through it. Like for example, if this was the LED and you're trying to drive LED and you wanted to know if this circuit can drive the LED or not, or if it is going to draw too much current or not, the best is you find the Thevenin equivalent for this. And again, you can see uh, for this part, the Thevenin is a better one to find because if you do um, a Norton, then you need to know the impedance of the VD for it to find out how much current is flowing through it, right? So I mean, you're taking it as a voltage source, but it is easier to find the Thevenins and just find the current through the RTH. So for this, what will be the Thevenin equivalent? What will be VTH? What is VTH? So VTH is, now I'm trying to find the Thevenin between these two nodes. So I remove obviously the diode, and then I look and find out what the open load voltage is. And in this case, because there's no current flowing through this, so it's essentially the voltage across these 2 points or the voltage right here. And so that will be V naught minus I naught times R naught. I think that's what a lot of people found out. So actually a lot of people just found out VTH, but that's not what I asked for, right? So they just ignored the diode. So that will be VTH. And then what's RTH? RTH is you open this, you short this, obviously that's R0 plus R1, right? Now you can apply this now. So this is now equal to V naught times I naught R naught. And this is R0 plus R1. And you apply the diode. And like Suman said, if I assume this is, let's say, around 0.5 volt or zero 0.6 volt, then you can measure this current, which is equal to V naught minus I naught R naught divided by R0 plus R1, right? And if you have the numbers, it actually, you just quickly find out, okay, this current is too high or too low and so on. So just wanted to show you that, when you have nonlinear elements in circuit like this, you can kind of remove it and make it linear and solve it. So I still apply the linear ones, but just have to be a little creative, okay? But you can't apply the node equation to the circuit itself without removing the diode because that's a nonlinear element. Okay, so that's what I wanted to talk about, the just analyzing simple linear systems. The other linear system we, especially in digital design, will be solving a lot is the RC time constant or the dynamic circuit analysis, which is typically RLC circuits, right? So here I have taken an example where you have a RC in parallel and you're taking a current source and you're applying this current source. So same thing, you apply your KCL, KVL here because those are still valid. These are still linear circuits. We proved that the capacitor is the linear element. And for these kind of dynamic circuits, because it's a differential equation, you have two solutions to it. And one part is called the homogeneous solution and the one part is called the particular solution. So people who are, control system centric, this homogeneous solution is really your poles of your system, and particular solutions are actually the zeros of your system. And then you take both of them in a transient sense, you take both of them and you actually add it. And this homogeneous part is the one which actually decides a lot of your circuit characteristics. That's why it's called characteristic solution, because that what is decides the nature of your circuit. For example, if I have this RC circuit, for example, if I change this I to some I naught plus I0 or something else, right? I keep the current source, but I change it. what will happen is your homogeneous solution will still remain the same because that's dependent only on your RC, but your particular solution will change. That's why I said. So in a S domain sense, your pole remained the same, but your zeros now will be different. Okay. So your homogeneous solution is basically making your independent source 0 and solving it. So your independent source was I of t, you make that 0 and you solve it. And if you solve it, you get the output VCH is equal to 8 to the power e to the power minus t over tau. And this tau turns out to be RC, which we call it as the time constant of this circuit. And your particular solution is you take a particular value of your I naught, right? And you solve it for that. So for example, if you take I naught, then one solution is VCP is equal to I naught R. This is a steady state solution, right? So you take that and you add it and you get both your solutions basically. I mean, you get your complete solution, your homogeneous and your particular solution. And you should always do, like I keep saying, you should always do sanity checks to make sure that this makes sense. So for example, you can see at time t equals to 0, if there is no initial condition here, so the voltage should be 0 across the capacitor. And you can see if you put t equals to 0, this becomes 1. 1 minus 1 is 0. And in steady state, once the capacitor is charged, then it's just I naught times R, this value, if your particular value of I of t is I naught. And you can see at t goes to infinity, this term goes to 0, then you get just I naught times R. Yeah, and for discharge analysis, it's the same, but now you have only homogeneous solutions. So for example, now you charge it and you remove this current source. So this cap is going to just discharge. So when it's discharging, basically it's just your homogeneous solution, which B of C of t is equal to I naught times R times e to the power minus t over tau, and that tau is still R over C. And like I just said, this is your characteristic solution, so that always remains the same. So now we removed the current source, and it is still tau is RC. So that's why it's called the characteristic solution of your this thing. And just want to show quickly some properties of the exponential. So for example, if you know the discharge, sort of the time domain curve for it, one way to find out, so this is how people usually find out experimentally what the tau is. If you know that it is a dominant RC, like there are no like series RCs and Elmore RCs and so on, then you find the slope at VC of equal to 0 at the point when it starts. That slope, wherever it meets the time axis, that's actually tau, which actually you can prove it from the equation as itself, because you take the derivative of it and make VC of equals to 0, and that gives you basically tau. Okay, and so, and some numbers, it's good to, especially if you're a digital IC designer, some numbers is good to have, as a rule of thumb. So when you're discharging at tau, it is 37% of your value at what it was at time t equals to 0. So from the peak, it's 37%. If you're charging at tau, it is 63% of your final value. So and that these are the numbers which are helpful when you're doing some quick calculations. Rise time, fall time, this is something you use a lot in doing characteristics of your digital time. So if you know that it is a RC system, and so rise time and fall times are from 90% to 10%. So let's say this is the fall time. So you find out the one second, let me switch so you find out what is the time difference from 90% of the peak value to the 10% of the peak value. That time is your rise time or fall time. And if you plug those values into the exponential equation, you'll see that that's around 2.2 times tau. So if you know tau, then you can say, okay, the rise time is going to be 2 times that. So for example, if your tau is a nanosecond, then your rise time is going to be approximately 2.2 nanosecond. And Puneet talked a lot about delays, right? So you have propagation delays and you have transition time. So this is transition time. So propagation delay is directly proportional to tau. So your propagation delay of inverter is usually the tau of your inverter. Your transition times are approximately 2.2 times tau. And this we don't use a lot in um, digital system, but again, it's good to know is if you really want your output value or input value to settle to almost 99% of the final value, then we allow at least 5 tau. And typically we use this a lot in analog where let's say we are doing A to Ds, and then if you know the A to D is like 8-bit A to D, then we say, okay, it needs to settle to around 99.94%, and say, okay, allow it to settle for 5 tau, and that'll be good enough. So that tells you about your clock frequencies too. So let's say you have a delay, you're creating a clock frequency and you want it to settle to almost 99%, then your clock frequency will be almost 2 times 5 tau, which is 10 tau of your delay. Okay. All right. So now, I'll just give just one example. And I was planning to do some, um, so, doing RC time constants for complicated RC networks. Like if you have series RCs and tree RCs, like clock tree synthesis, the clock tree is literally a tree of RCs. So how do you find delays in that? And I think what we'll do is we'll do that um, when we are doing the delays. Okay, so the inverter characteristic when Santanu is doing the delays, that is the time I think it'll make sense to cover that. So that way, hopefully by that time, I don't know if you've done layout or not, but uh, just give me a second, 1 second. So I'll just do a quick problem. So here I'm asking you guys to do the rise time, fall time by inspection. Okay, so what I mean by inspection is I don't want you to solve the differential equation. Okay, so with all the tools we have used so far and whatever you know about um, RC time constants, what do you think? So here what I'm asking about the rise and fall time is basically the 5 volt and the 1 milliamp are step response. So essentially at time t equals to 0. So maybe I should make that clear. So at time t equals to 0, the voltage source V naught goes from 0 to 5 volt, right? And the current source I naught goes from 0 to I naught. So this goes to 5 volt, this goes to 1 milliamp. Okay, and what so obviously this is a first order system because I have only one cap. So the output is going to have will start from 0 and go some final value, right? So I want you guys to find out what this final value is. So VC at infinity, and what is the time constant for it? Rise time, fall time, which will so basically TR and TF, TR and TF, and that will require you to find the tau as well. Okay, so let me give you guys a couple of minutes and see. And like I said, don't try to solve the network equation, but do it by inspection in the sense that convert it into a equivalent RC circuit or whatever you can, and then tell me what the rise time, fall time would be. So this, which formula are you talking about? Time constant is RC, right? And that's what I want you to find. What is this RC? Yeah, time constant is R times C. Okay, so by the way, everyone is writing 2 nanoseconds. Is that tau or rise time, fall time, or and you have to find out the VC of infinity too. Like what is the voltage across the capacitor at steady state? Okay, steady state 4 volts. Okay. Okay, maybe one of you can come online and just quickly explain how did you solve it. So Sandharan, can you come online and explain how did you solve it?
To calculate the time constant, I multiply the R into C. First, where C is placed, I open circuit. First, I um, deactivate all the sources, means short circuit the voltage source and open circuit the current source. Then I place a open circuit where C is placed. Then find the R equivalent. Then it is 2 kilo ohm. Then I do RC.
Okay, good. Perfect. And how about V of infinity? How did you do that?
Sir, I am calculating that. I am not.
Okay, all right. And how about you show this? How did you solve it?
So, firstly, I take that Thevenin transformation.
Hmm.
So the source voltage I am getting is 4 volt, and with a resistor of 2 kilo ohm in series. So
Okay,
basically, when we are calculating for steady state, the source voltage will be the same as the capacitor voltage, I guess. So that's why at steady state it will be 4 volt.
Okay, perfect. Yeah, that's good. Yeah, so while others are solving, I think so this got it right. So I mean, what Sandharani said is perfectly fine too. So if I'm asking you to do time constant, then that's what's called the open circuit time constant. So you take your capacitor and you make all your voltage sources and zero and current sources zero. So the voltage sources become short, current sources become open. And so find out what the resistance across the capacitor is. And in this case, it's 2K. So 1 perf times 2K is 2 nanosecond, right? So tau is equal to 2 nanosecond. And steady state voltage, obviously, you can find out by just opening the cap, because at steady state, the cap is open. And it is basically V naught minus I naught time R naught, because there is no current flowing through this R1, which we've already solved, right? So which is 4 volt, like what Swadesh shared. But yeah, the Thevenin actually gives you a better picture, because once you do the Thevenin, then you get a VTH, which is 4 volts, and RTH, which is 2 kilo ohms, and that's your cap. So from this, you know that your step input is actually 4 volts. So your output is just going to follow that and steady state will be 4 volts. Uh, um, and the tau is equal to 2 nanoseconds. So rise time and fall time are going to be 2.2 times 2 nanosecond, which is 4.4 nanosecond, right? So that's what I had asked for. Okay, good. Now let me ask you this question. Let's see if you got the homogeneous and this part fine. Now I'm going to make this 5 volt to, let's say, 4 volts, and I'm going to make this 1 milliamp to like 2 milliamp. Okay. And then again, do the step thing. And what will be the time constant now?
So what is the question? Please repeat.
So the question is, what I'm saying is that I change this 5 volts to 4 volts now. So instead of stepping to 5 volts, it's going to step to 4 volts now. And instead of this stepping to 1 milliamp, it will step to 2 milliamps now. So my question now is, what's the time constant for this new circuit right now? So the new circuit is, so Rudranarayan says same, will be the same, same. Okay, good. Why it is the same? Because your characteristics equation hasn't changed. Your RC is still the same, right? Because if you do the Thevenin again, this part is going to change now, but this is still going to be 2K, right? So that's another way to look at it. So correct. So again, in control systems language, when you change independent sources, your zeros change, which is basically saying your final value will be different, but your pole will just remain the same, which is, you know, RC in this case. Okay, good. All right, so I think we'll stop here. And like I said, um, the RC, the Elmore resistance and all that, will probably do that when we are doing delays for combinational gates and inverters. I think it'll make more sense to do it then. Okay, so any questions on any of this basic material we just covered? Like I said, it's just a review of some of the basic material, but it's good to sort of, because these are some of the most important ones which you are going to use most of the time. The rest of, you know, other 1,000 principles you learned are, either you can reference them, or mostly you don't need them, or you can derive from here. So, all right, any other questions before we sign off? So tomorrow, like as we said before, in the morning session, so Santanu has a very good presentation on doing the modeling of, how to do the spice modeling. So he's going to cover that. And in the second half, what we'll do is we'll have a Q&A. It's basically just to review all the stuff, like everything we have, um, the passive devices, the MOS transistors and MOS modeling, whatever we have. So might take some problems, but the best is, if you have any doubts, that'll be the best time to ask. So we just review it before we start doing the lab on Friday. So I think second half will do that. Okay. So Santanu, do you want to add anything or?
No, sir. So just I'm saying